When addressing a breaker oversizing issue for a 2 kVA transformer operating at 480 volt single phase with a 30 k amps available fault current upstream, several solutions can be considered. The primary concern is that the calculated primary breaker size is 12.5 amps based on 125% secondary protection, but the smallest available breaker with sufficient interrupting capacity is 15 amps, exceeding the 300% limit. Firstly, upsizing the transformer is a viable option. Increasing the transformer's kVA rating will reduce the primary current, thereby allowing for the use of a smaller, more appropriately sized breaker. For example, if a 3 kVA transformer is used instead, maintaining the same voltage, the primary current would decrease to approximately 10 amps. This would make it possible to protect the primary side with a 15 amps breaker, bringing the protection within a more acceptable range. Secondly, consider using fuses instead of circuit breakers. Fuses generally possess a higher interrupting capacity compared to circuit breakers, which is advantageous when dealing with high available fault currents. In this scenario, select fuses with an interrupting capacity that exceeds the available fault current, such as 50 k amps. Ensure that the fuse rating is appropriate for the transformer's primary current, aligning with the 125% overload protection requirement. Fuses offer a reliable and precise method of overcurrent protection. Other important factors to consider include checking the availability of breakers, adjusting fault current, considering secondary protection and transformer tap settings. Verify with manufacturers whether circuit breakers with lower amperage ratings and higher interrupting capacities are available, either as special orders or in different product lines. It is worth exploring all potential sources to find a breaker that meets the specific requirements. If feasible, evaluate the upstream circuit to determine if there are measures that can be taken to reduce the available fault current. This might involve adding series impedance to the circuit or adjusting the settings of protective relays. Reducing the fault current can make it easier to find a suitable breaker size and improve the overall system protection. Enhance secondary protection measures such as motor starter overloads to limit surge currents that could potentially contribute to primary overloads. Implementing robust secondary protection can help prevent use and stripping of the primary breaker and improve the transformer's operational reliability. Determine if the transformer has adjustable voltage taps. Lowering the secondary voltage tap can reduce the primary current, which may allow for the use of a smaller breaker. Carefully evaluate the impact of tap adjustments on the secondary voltage and load requirements before making any changes. In summary, to address the breaker oversizing issue, consider upsizing the transformer to reduce the primary current or utilizing fuses which offer higher interrupting capacity. Also, explore the potential solutions such as checking breaker availability, adjusting fault current, enhancing secondary protection, and evaluating transformer tap settings. Each of these approaches can contribute to optimizing the protection scheme and ensuring the reliable and safe operation of the transformer. Consider the NEC or other local regulatory requirements. NEC Section 450.3 outlines the overcurrent protection requirements for transformers. For transformers over 600 volts, the primary side protection should be set at no more than 125% of the rated primary current if using a circuit breaker and no more than 250% if using a fuse. For transformers under 600 volts, the primary protection should be set at no more than 250% of the rated primary current if the secondary protection limits the loading to code-defined levels and 125% if the secondary protection does not limit the load. NEC Section 240.4 decovers conductor protection. This section restricts using the next highest standard overcurrent device for protecting conductors rated over 800 amps. However, for smaller conductors, it is permissible to use the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device size. Standard ampere ratings for fuses and inverse time circuit breakers are listed in NEC 240.6. These standard sizes should be considered when selecting the appropriate overcurrent protection. Interrupting rating refers to the maximum fault current that an overcurrent protective device can safely interrupt. Circuit breakers and fuses must have an interrupting rating sufficient for the available fault current at their point of installation. NEC 110.9 and 110.10 cover interrupting rating and circuit impedance and other characteristics, respectively. Coordination involves selecting and arranging overcurrent protective devices to minimize disruptions when an overcurrent event occurs. The goal is to have the protective device closest to the fault open first, isolating only the faulted portion of the system. This minimizes downtime and enhances safety. Selective coordination studies are recommended for critical systems. For a 2 kVA transformer with a 480 volts primary, the primary current can be calculated using the formula I equals kVA times 1000 divided by voltage. In this case, I equals 2 kVA times 1000 divided by 480 volts, which equals approximately 4.17 amps. According to the question, the primary protection requires a 12.5 amps breaker, which is 125% of the secondary. This suggests that the secondary current and the transformer impedance are influencing the primary protection requirements. The initial calculation of 4.17 amps as the primary current seems low for a 2 kVA transformer at 480 volts and may indicate a misunderstanding or missing information in the problem statement. The information provided that the primary needs a breaker of 12.5 amps based on 125% secondary protection suggests that the transformer's secondary characteristics and the load it serves significantly influence the primary protection requirements. If the secondary load is such that it necessitates a 12.5 amps primary breaker for adequate protection, this requirement must be carefully considered. The available fault current of 30 kA upstream is a critical factor. The selected overcurrent protection devices must have an interrupting rating equal to or greater than this value to ensure they can safely interrupt any potential fault currents. Given that standard breaker sizes may not exactly match calculated values, NEC 240.4 B allows for the use of the next higher standard overcurrent device rating if the calculated value does not correspond to a standard size, provided certain conditions are met. However, this allowance must be applied judiciously and in accordance with the code. If a 15 amps breaker is being considered due to the unavailability of a 12.5 amps breaker, it is essential to verify that using the larger breaker complies with all applicable codes and standards. The primary purpose of overcurrent protection is to protect the transformer and the connected conductors from damage due to overcurrents. The overcurrent device should be sized and selected to provide this protection while also preventing nuisance tripping. In the context of the problem, where 15 amps breaker exceeds the 300% limit, it is crucial to ensure that this choice does not compromise the safety or reliability of the system. If upsizing the transformer is considered, the new transformer's kVA rating should be selected based on the actual load requirements and future expansion plans. A larger transformer will have a higher primary current rating, which may allow for a more appropriately sized breaker. If fuses are chosen, they must be carefully selected to match the transformer's primary current rating and to provide the necessary interrupting capacity. Fuses generally offer faster response times to overcurrents compared to circuit breakers, which can be advantageous in certain applications. Exploring options for reducing the available fault current upstream can be beneficial. This could involve installing current-limiting reactors or other impedance devices to reduce the magnitude of the fault current at the transformer's primary terminals. Reducing the fault current can make it easier to select suitable overcurrent protection devices and improve the overall system coordination. The secondary protection of the transformer is an important consideration. Ensuring that the secondary side is adequately protected can help prevent overcurrents from propagating to the primary side. This may involve using appropriately sized fuses or circuit breakers on the secondary side, as well as implementing other protective measures such as motor overload relays. Transformers often have adjustable taps that allow for fine-tuning of the voltage ratio. Adjusting the tap settings can affect the primary current and may allow for a smaller breaker to be used. However, It is essential to ensure that the secondary voltage remains within acceptable limits after adjusting the taps. To accurately assess the transformer protection requirements, it is necessary to have a complete understanding of the system parameters, including the transformer's impedance, the connected loads, and the available fault current. A thorough analysis of these factors will help ensure that the selected overcurrent protection devices are appropriate and effective. In some cases, it may be necessary to consult with a qualified electrical engineer to perform a detailed coordination study. A coordination study can help ensure that the overcurrent protection devices are properly coordinated and that the system is adequately protected against overcurrents and fault currents. Consider that the scenario involves a 2 kV transformer operating at 480 volts single phase with a 30 kA available fault current upstream. The primary protection requirement is a 12.5 amps breaker based on 125% secondary protection, but only a 15 amps breaker is available, which exceeds the 300% limit. Given this, it is important to revisit the fundamental calculations and assumptions to ensure accuracy. The primary current of a 2 kVA 480 volt single-phase transformer can be calculated as follows. I equals kVA times 1000 divided by voltage, so I equals 2 times 1000 divided by 480, which results in approximately 4.17 amps. This calculated primary current is significantly lower than the required 12.5 amps breaker size indicated in the problem statement. This discrepancy suggests that there might be additional factors influencing the breaker size selection, such as specific load characteristics or code requirements. The initial step is to verify the accuracy of the 12.5 amps breaker requirement. This can be done by reviewing the transformer's nameplate data, the connected load characteristics, and any applicable code requirements. It is essential to ensure that all relevant factors are considered when determining the appropriate breaker size. If the 12.5 amps breaker requirement is indeed accurate, then the next step is to explore alternative solutions that can address the oversizing issue. One option is to use fuses instead of circuit breakers. Fuses typically have higher interrupting capacities and may be available in sizes that are closer to the required 12.5 amps rating. When selecting fuses, it is important to ensure that they are properly rated for the application and that they provide adequate protection for the transformer and the connected conductors. Another option is to upsize the transformer to a larger kVA rating. This would reduce the primary current and may allow for the use of a smaller breaker. However, it is important to carefully consider the load requirements and the available space when upsizing the transformer. It is also important to ensure that the larger transformer is compatible with the existing electrical system. In addition to these options, it may be possible to adjust the transformer's tap settings to reduce the primary current. However, it is important to ensure that the secondary voltage remains within acceptable limits after adjusting the taps. It may also be possible to reduce the available fault current upstream by adding impedance to the circuit. This would reduce the stress on the overcurrent protection devices and may allow for the use of a smaller breaker. When considering these alternative solutions, it is important to consult with a qualified electrical engineer to ensure that the selected solution is safe and effective. The engineer can perform a detailed analysis of the system and can provide recommendations based on the specific requirements of the application. Also consider the NEC or other local regulatory requirements. NEC Section 450.3 outlines the overcurrent protection requirements for transformers. For transformers over 600 volts, the primary side protection should be set at no more than 125% of the rated primary current if using a circuit breaker and no more than 250% if using a fuse. For transformers under 600 volts, the primary protection should be set at no more than 250% of the rated primary current if the secondary protection limits the loading to code-defined levels and 125% if the secondary protection does not limit the load. NEC Section 240.4 D covers conductor protection. This section restricts using the next higher standard overcurrent device for protecting conductors rated over 800 amps. However, For smaller conductors, it is permissible to use the next higher standard overcurrent device rating if the conductor ampacity does not correspond to a standard overcurrent device size. Standard ampere ratings for fuses and inverse time circuit breakers are listed in NEC 240.6. 8. These standard sizes should be considered when selecting the appropriate overcurrent protection. Interrupting rating refers to the maximum fault current that an overcurrent protective device can safely interrupt. Circuit breakers and fuses must have an interrupting rating sufficient for the available fault current at their point of installation. NEC 110.9 and 110.10 cover interrupting rating and circuit impedance and other characteristics, respectively. Coordination involves selecting and arranging overcurrent protective devices to minimize disruptions when an overcurrent event occurs. The goal is to have the protective device closest to the fault open first, isolating only the faulted portion of the system. This minimizes downtime and enhances safety. Selective coordination studies are recommended for critical systems. When addressing the challenge of selecting an appropriate circuit breaker for a 2 kVA transformer operating at 480 volt single phase with a high available fault current of 30 kA upstream, it's essential to methodically evaluate all available options and considerations. The primary issue is that the calculated primary breaker size of 12.5 amps, based on 125% secondary protection, cannot be met because the smallest available breaker with a sufficient interrupting capacity is 15 amps, which exceeds the 300% limit. This situation requires a comprehensive approach to ensure safety and compliance with electrical codes and standards. Firstly, it's important to revisit the initial calculations and assumptions to confirm their accuracy. The primary current for a 2 kVA transformer at 480 volts can be calculated using the formula I equals kVA times 1000 divided by voltage, which results in approximately 4.17 amps. This calculated primary current is significantly lower than the required 12.5 amps breaker size stated, suggesting that there are additional factors influencing the breaker size selection. Secondly, verify the 12.5 amps breaker requirement by reviewing the transformer's nameplate data, the characteristics of the connected load, and any applicable code requirements. Ensure that all relevant factors are considered when determining the appropriate breaker size, as there might be specific load conditions or code stipulations that necessitate a larger breaker. If the 12.5 amps breaker requirement is indeed accurate, explore alternative solutions to address the oversizing issue. Fuses, with their generally higher interrupting capacities, can be a viable alternative to circuit breakers. Check if fuses are available in sizes closer to the required 12.5 amps rating. When selecting fuses, ensure they are properly rated for the application and provide adequate protection for the transformer and connected conductors. Thirdly, consider upsizing the transformer to a larger kVA rating. This would reduce the primary current and potentially allow for the use of a smaller, more appropriately sized breaker. However, carefully consider the load requirements, available space, and compatibility with the existing electrical system before upsizing the transformer. Fourthly, explore the possibility of adjusting the transformer's tap settings to reduce the primary current. Before doing so, ensure that the secondary voltage remains within acceptable limits after adjusting the taps, as this could affect the performance of the connected load. Another potential solution is to reduce the available fault current upstream by adding impedance to the circuit, using devices like current limiting reactors. Reducing the fault current can ease the selection of suitable overcurrent protection devices and improve the overall system coordination. Carefully consider the secondary protection of the transformer, ensuring that the secondary side is adequately protected. This can prevent overcurrents from propagating to the primary side. Appropriately sized fuses or circuit breakers on the secondary side, along with protective measures like motor overload relays, can enhance secondary protection. Consulting with a qualified electrical engineer is advisable to ensure that the selected solution is safe, effective, and compliant with all applicable codes and standards. An engineer can perform a detailed analysis of the system and provide recommendations tailored to the specific requirements of the application. Lastly, consider the NEC or other local regulatory requirements, which provide guidelines for transformer protection and overcurrent device selection. Adhering to these requirements ensures that the electrical system is safe and compliant. In summary, addressing the breaker oversizing issue for a 2 kVA transformer involves a systematic approach. Begin by verifying calculations and requirements, explore alternative protection methods like fuses, consider upsizing the transformer or adjusting tap settings, and consult with an electrical engineer to ensure a safe and compliant solution.